Now the compiler's going to be like, no, you try to, you can't, first of all, we don't even get as far as this line, right? What it says is, you made a reference to x. Sorry, as long as that reference to x is live, which is what y is, you can't get rid of x. X can't get rid of its value. It's not allowed to drop it that early. So y has to outlive x. It can't, x can't, x can't live less long than y does. And by proving that that could happen, right? By not being able to prove that that x outlives y, that x lives longer than y, at least as long as y does. By not being able to prove that, the compiler's like, I can't prove that, because it's not true in this case. It's like, no, sorry, this is baloney. In C, this would just be a dangling pointer, and then at the end I would print, whatever y was pointing at, storage-wise, right? That address wouldn't change. This is all perfectly legitimate, right? C, C++, except that I'd use delete or free here. I'd use new up there, and I'd change the syntax a little bit. Yeah? Yeah? So that's today's fundamental truth, is that the compiler's keeping track of all this stuff for you, and that, it's gonna annoy you mercilessly. You're like, I know what I want to do, and you're not letting me do it, you stupid compiler. Well, it's because what you want to do isn't actually what you want to do, it's just what you thought you wanted to do. You have to figure out what you really want to do now. Yeah?
If we refer to x after the print line y,
Yep.
would,
It won't let you. It'll be like, X is gone. You dropped it. It's moved out of
we
there.
didn't have the x.
What?
You had to drop x, sorry.
If we don't drop X,
Yeah, if you don't drop x, would it work still?
yeah, we're fine. X and Y are both in scope until the end of the function. I can say things like this. Let's see what happens when I do this. I know what's going to happen. It's going to fail to compile, but for a weird reason, and we can fix it really easily. It's like, you know what? There is no equality operator for boguses. Guess how we fix that? We derive partial eq and eq for these. And since strings have partial eq and eq, then so do boguses now. And it's like, but wait a minute. One of those is a reference. The other one isn't. We could fix that with fancy type stuff too. It's probably easier to just say pointer to y, right? Hey, there we go. And yeah, everybody's perfectly happy. Notice how much hassling with the compiler you do in this language when you're starting out. Notice, I could have avoided all those hassles because I saw them all coming, but for a beginning Rust programmer, that's part of the game. It's just going, you know what? I didn't see that coming. The compiler's whining about a thing I never even thought about before, and then you have to think about, why is it whining? How can I fix its whining? And that's time when having a Slack channel. This is sort of what you're paying for in this course, is having a fancy Slack channel plus Mark blabbing at you once in a while. That's all you get over just buying the book and working through it. So take advantage of that. Somebody had a question?
Yeah. If we had tried to derive copy here,
Yeah.
string isn't copy.
Yeah, we did try. And it said, no, string's not copied.
Right, but you had an implicit copy in the code. Like, will it
Before I had a string field, I had a copy, and it was fine, yeah.
Yeah, so if you add copy like to the derive statement, and you don't try to do an implicit copy, will it compile or will it complain that you're trying to derive something?
No, it'll still complain. It won't let you derive a copy in the first place because it's not sure, where you might use the struct, right? So it's like, no, that's not a thing. Here we're not trying to copy at all, and yet still, no answer. That's a great question. I understand what you're asking for. No. It's the Rust compiler errs on the side of caution an awful lot. Language is designed to let you not write things that you probably will wish later you hadn't written. And so, there you are. I don't know if I need those underbars, by the way. I sort of feel like I'll get a warning if I don't put them there. Those are the ignore whether this is used or not thing. it's pretty clear that that field is used in the sense that we create a thing with it, but we never actually do anything with that field, so I'm not sure if we'll get a warning if we get rid of the underbar there. Kind of feel like we'll get a warning about field is never used. Let's find out. By the way, field is a terrible field naming. You should never name things like that.
Doesn't print use it?
Good question. I don't know. Oh yeah, it's perfectly happy. Never mind. There, I feel better now. So that is a very, very short form ownership tutorial. Yeah.
Why do we not lose ownership of X in Printline?
Because Println borrows it. Println is a macro, and one of the things that macro does is it doesn't actually move X into anything. It just moves, it takes its address. That's part of the macro magic. And so that's actually, X and Y are actually being taken by reference there. That's an excellent question. Yeah, they're being taken by reference. Well, you can see that.
So in general, I guess, for like standard library stuff or whatever, we assume that it's not going to take the reference away when we pass it in for.
Oh, no. Println's special in this regard. For most functions, it'll tell you whether it takes a reference or a value, and you have to give it the right thing. This isn't C++, so I see what you're asking. It's a really good point. In C++, you can declare things of reference type, and you don't have to put ampersands on front when you call them, because the compiler figures it all out somehow. No, Rust doesn't do that. If it wants the address of something, you have to pass the address of something explicitly. There's no secret references. And so the functions mostly tell you. The only kind of secret reference is here because it's a macro and because it's so much more convenient not to have to stick ampersands on the front of things. They're just like, yeah, you know what? No, we're just gonna do it. So yeah, great question. It shows me you really understand what's going on about ownership. That should have moved X, and then I shouldn't have been able to use it later, but it doesn't because magic. Yeah.
Is there a way to take a reference to something, like a reference to an array, for instance, and make a mutable copy of it?
Absolutely. And the way you would do that normally for arrays in specific is you would clone. You'd make a clone that you own, right? So let's actually make a clone of this string and mutate it. That's actually very straightforward. Let mute xm, another terrible name. All my names in these programs are awful. X dot clone. I've now made a clone of the bogus. Oh, sorry. Yeah, it's not a clone just of the string, it's of the whole bogus, right? A clone that's mutable. The original X is not disturbed, it doesn't care. XM now owns the copy, X still owns the original, right? And now I can do stuff like xm.field plus equals exclamation point, right? That's an exclamation point? Yeah, I should get all this up. And we'll copy paste code here, which is terrible. You should never ever do that. And this should work fine. And sure enough, the mutable clone, right? I was able to mutate. It was perfectly happy with it. The immutable original, I didn't mutate, and it stayed the same value. So everything worked kind of the way you might expect. Other questions?
Well, I guess I'm curious because in the program for the homework that we were writing, we're passing in the ampersand nums array.
Yep.
And when you try to make some slice copy of that,
Yep.
it tells you can't because, well, if you wanted to have something that was mutable, it tells you that you can't because the ampersand nums is not a mutable type.
Right, you can't make a mutable copy of the reference itself, right? Because the reference was pointing to immutable data. But you could have used clone to actually clone the whole array and make a new copy of the whole array.
I see.
If you look at the median example, the median one, I actually did that for you. If you look at that code that I gave you, it starts by cloning the slice so that you can sort it, to get a mutable copy that you can sort, which is terribly inefficient, but that's the thing. I wasn't going to do some fancy median algorithm, I just cloned the array. And so yeah, you can see an example of that in there. And that's why I did that clone. I did the clone because I needed a mutable copy so that I could sort the thing in place without disturbing the original. So I was allowed to disturb the original.
You did a two owned.
Oh, two-owned is effectively a clone. Sorry, there's a lot of ways to write that. Clone would have worked there fine. Yeah, God, what a mess. So, there's 3 ways, it turns out, to make a copy of a string specifically. There's clone, and there's two-owned, and there's two-string. And they all do the exact same thing. They all make a copy of a string. If you give them a string, they turn that string into a copy of the string. So why would you use one versus the other? There lies the source of many, many arguments and debates on Reddit, I promise you. And there are people who feel very, very religiously that two-string is an abomination that you should never use. There are people who feel very, very religiously that two-owned is the only true way, and you should never clone a string. All those people are insane. You should just be aware that there are these 3 things. So the more full version of that crazy sounding story I just gave you will be later in the course when we talk about traits. And it will become more obvious why there's 3 ways to make a copy of a string, and 2 ways to make a copy of an array, clone and two-owned. The very, very short version is that I could derive clone for my bogus, or I could implement the two-owned trait for my bogus, depending on what I wanted to think of the bogus as being like, and they have a little bit different other methods. And some things work with one, and some things work with the other, but they both provide a way to make a copy, which is super, super annoying, and welcome to us funny melange of types.
When you declare a variable to be mutable, can you later in your program make it not mutable without closing it?
Yeah, absolutely. So let's do that. Let's just make it not mutable right here when we're done mutating it. I can say let xm equal xm. Wait, what? How did that do anything? Well, remember, those 2 xm's are 2 different variables, right? The first xm was a variable I explicitly marked mutable. The second xm is a variable that I marked immutable. And what happens to the owned value in the first xm? Oh, it moves into the second xm. So there's a notional move here, but as you might guess, the compiler's optimizer is pretty good about figuring out in cases like this that it doesn't actually have to put a memcopy anywhere. There's no storage actually moving around here. It's just the ownership of the storage changes from the first variable to the second. And we can prove that does the right thing, because it makes even me a little uncomfortable to believe my silly story until I've tried to add another exclamation point onto the thing. I think at this point I'll get an xm is not mutable error. Sure enough, can't borrow the field is mutable. Hey, you might want to put a mute there. Okay, good. That was one. So yeah, there's ways to do this thing, but like so much of the stuff we've been talking about and so much of the stuff we're going to talk about, it's not always super obvious. There's this whole mechanism here. It looks like I just removed the mute. Kind of. I declared a new variable with the same name and moved the value from the old. It's like a lot's going on under the hood, but the result's pretty simple. It's like, okay, I got rid of the mute now. You don't ever normally do that. Usually if you want a thing to be mutable, you want it to be mutable for the whole scope, and so you just declare it mute. Don't worry about it too much. Try to be careful. I mean, mute's one of those flags like unsafe, only more mildly so. What it really says is, oh, I'm going to change this. I've taken on a whole new set of responsibilities. I need to be more careful. It's like a little warning flag that tells the compiler, it's sort of a very minor hold my beer, hold my Coke, right? It's sort of, hold my Coke. I'm going to make this mutable and change it around. And the compiler's like, okay, you said you wanted to be able to mutate it. Now you can mutate it. I don't care. But it just makes you responsible for more stuff. Makes sense? Yeah. Almost all the automatic conversions you would think happen. So can I take a mutable reference to an immutable reference to a mutable variable? I absolutely can. I don't have to say ampersand mute because the variable's mutable. I can say ampersand. The compiler's like, okay, you've now got an immutable reference to a mutable variable. Congratulations.
said this, but does drop take the value or the address of its argument?
The value, because that's the whole point. You're moving the value into the drop as an argument, and that's how it gets rid of it. It moves the value into the drop. The drop says, I have nothing to do with this, including return it, so I'm going to free it, and then it frees it. Yeah.
It frees the memory, or?
Frees memory, yeah. There's a call, the compiler sticks a call to free that's invisible in the body of drop. We can make our own drop. It's really, really easy. Fun my drop. It's easy up to a point. I'm going to make it take an arbitrary type to drop. This is advanced Rust in a way. There, it can take a value of any type and drop it. And the body of this is, oh wait, I don't actually have any body. Okay, and now I can my drop X. And when I call my drop, it's going to move X, the value owned by X, into the parameter of my drop. My drop's like, well, I don't have anything to do with this. So the compiler sticks an invisible free right here, because after all, I'm not using the stuff, I'm supposed to let it go. And now I've dropped the value. So let's do that. It's like, no. It behaves just as if I'd called the system drop. The system drop is literally written just like this. That's silly, we shouldn't do that. But that's how it works. And if you go look at the source code, like I say, if you don't know what's going on, if you're not like, I understand this Rust thing, you're like, that's dumb. How does this function with an empty body do anything useful? Well, it does because the compiler sticks code in it. Okay. A little time left. We end at 3:20? All right, let's talk a little bit about, for the time that's remaining, sorry, I know the second span, I've been taking the first break a little early with the intention of taking 2 breaks, and then we always run out of time to take the second break. So somebody should probably bug me at about, I don't know, 1:45 or something, we'll take another 5-minute break. That second span gets a little long. These 2.5-hour classes are silly is what I guess I'm saying. So we talked about ownership. The C++ name for this is Resource Acquisition as Initialization, which is a really, really dumb name that goes to a really dumb abbreviation. But it's the idea of anytime you declare a variable, you also get, allocate the storage for that variable and initialize it. Mutability, we've talked about that pretty heavily. I should point out that copy and clone and mute are all deep, in the sense that if I have a struct that contains another struct that contains a third struct as a variable, when I say that the variables mute, all of that internal contents is mutable. When I say clone, it makes a copy of everything all the way down. When I say copy, then it feels free to make a copy of that whole mess, no matter how much deeply nested structure is in there. That's a big difference from a lot of languages where copies are shallow by default. C++. There's no good way to get a shallow copy of Rust. And the reason that they made everything deep copy and deep mute and whatever is because the static analysis just is hard to make work if you don't do that. So for safety purposes, it turns out to be better. But watch out for that. It's a thing that's going to happen. It's normally a feature, but when it's a bug, it's a real bug. So yeah. Oh, lifetimes. Oh, geez. Is there something else we could talk about? Oh, references. Yeah, we should talk about references instead. References are good. We'll go back and talk about lifetimes on Wednesday, because that's not a topic to start into 5 minutes before the end of class. So there's 2 kinds of references you can take to an owned thing. There's immutable references, just ampersand, and there's mutable references to mutable things, right? Ampersand mute, right? And I can always choose whether I want an ampersand or an ampersand mute reference to a thing. But in either case, right, we have this obligation that the thing that you're referring to live at least as long as the reference itself. You can't let the thing that's being referred to go and leave a pointer dangling. The compiler checks that. But the compiler has another rule, which is super important that you have to keep track of. You can make as many immutable references to a thing as you want. You can make multiple read-only references. Or, and these are mutually exclusive, or you can make a single mutable reference, a single writable reference. And while you have that writable reference, the writable reference is the only place you can change that thing from. You can't change it from the original. So if I loan out, and this terminology is all standard Rust terminology, even though it's kind of cutesy and terrible, right? If I loan out my ownership with ampersand, sure, I can give that to everybody. They can all look at it through that pointer. We're all good. And my only obligation is that I mustn't move or drop that value while there are still pointers to it outstanding. The compiler checks that at compile time, and if it can't prove that my value's alive at least as long as all those pointers I gave away, then it fails my program. Make sense? The mutable situation is a little weirder. If I own a mutable value, if I own a value mutably, and I give away a mutable pointer to it, well, first of all, I must not have previously given out any readable any other kinds of pointer. So there can be at most one mutable reference to a value, and you can't have any other immutable references. And so that when I loan out a mutable reference, I'm effectively temporarily giving up ownership. I can't do anything with the value. I can't read it, I can't write it until that mutable reference is gone. Why? Well, for the same rule that we have reader-writer lock, reason we have reader-writer locks in databases, right? It's the idea that I don't want to have weird race conditions where what value I get from reading the variable depends on what something far away has done that might even be in another thread. I don't want to be there. I certainly don't want things fighting over the variable, that